What is LiDAR? How was LiDAR created? How is it used? And how much does LiDAR cost? These are important considerations for the prospective buyer. LiDAR is an acronym standing for Light Detection and Ranging. Depending on the application and region, it may also be called laser altimetry or airborne laser scanning. It is important to realize that LiDAR is a system. It is a series of components working together to provide three-dimensional information, usually over a large area. The key components of a LiDAR system are the laser emitter receiver, the inertial measurement unit, GPS, and an onboard computer. In a scanning LiDAR system, another important component is the scanning mirror. Scanning LiDAR is the kind most commercial vendors use. The laser is the primary sensor in the LiDAR system. The laser is used to record the distance to a target. This is accomplished by emitting pulses of laser light. The pulses travel down from the platform, reflect off the target, and the energy is returned to the collector. The laser can fire thousands of pulses per second. Recorded pulses are called postings. As the laser or its platform moves, these postings form an irregular pattern where they strike the target. This is measured in average number of postings per unit area. In a scanning LiDAR system, the laser is in a fixed position and fires at a mirror that scans at high speeds to direct the pulses to the target. The next component is the inertial measurement unit. It may also be called the internal navigation system. This component is attached to the laser scanner and records the orientation of the LiDAR platform during pulse firings. The next component is the GPS, or Global Positioning System. Just as with commercial units used in automobiles, the GPS provides the location of the LiDAR platform. Commercial LiDAR GPS systems are accurate to within several inches. Coupled with the inertial measurement unit described previously, this provides very accurate information on both the location and orientation of the LiDAR platform. The final major component of the LiDAR system is the onboard computer. This records all the data from all the systems and sensors and converts it into millions of XYZ coordinate points. All these components together, the laser, the IMU, the GPS, and the computer, are the basic units of the LiDAR system. From the LiDAR platform, the laser fires thousands of pulses to the ground every second. The scanning mirror detects these pulses in a swath following the flight path. These are reflected back to the onboard detector where distance to target is measured. Coupled with the location and orientation information from the IMU and GPS, the onboard computer can then accurately convert the pulse returns into X, Y, and Z coordinates. These points are the primary LiDAR product and collectively referred to as a point cloud. In addition to the coordinate and elevation data for each point, LiDAR data usually includes other embedded information as shown here. This can vary by vendor, sensor type, and applied processing, but the information can be useful for a variety of applications. There are many different varieties of LiDAR for many different applications. For example, the LiDAR platform may be space-based, an aircraft, or ground-based. Commercial LiDAR is evolving constantly, but the most common systems are airborne, scanning, able to record multiple returns per pulse, and have relatively small footprints and high posting densities. We've previously demonstrated airborne scanning LiDAR, where the laser pulse is directed by a mirror. The LiDAR footprint refers to the diameter of the laser beam pulse where it strikes the target. Small footprint LiDAR usually ranges from about 1 to 1.5 feet in diameter. Smaller footprints produce a higher resolution and usually a higher density point cloud. Multiple return LiDAR means that for each laser pulse, the detector may record more than one return. For example, in a forested area, portions of a single LiDAR pulse may be reflected back as the pulse strikes the tree top, while more of the pulse is reflected back from further down, and so on, until striking the ground. The ground return is called the last return. Posting density refers to the number of recorded pulses per unit of area. Data densities range from approximately 5 meters between points to over 10 points per square meter. The data density required depends upon the application. The LiDAR point cloud is the primary product. However, once collected, various types of post-processing are usually performed on the point cloud to make the data more useful to specific applications. Processed products or deliverables will vary by application, but some common ones include further classification of the point cloud, such as subsetting first and last returns, and more refined classification, such as the objects from which the return reflected, for example, buildings, asphalt, or vegetation. Other surfaces and products include intensity imagery, which is based on the energy intensity of the return. Bare earth products, such as mass point vector files or digital elevation models, can be created by filtering ground returns from point clouds. Contours are usually time and labor intensive and in many cases require several additional data sets to produce. Finally, quality assessment and control is an important aspect of the LiDAR product. This includes both qualitative aspects such as general product completeness, as well as quantitative measures such as ground control points. To determine if the LiDAR data meets the required quality specifications, control points are assessed in the project area and compared with the LiDAR return values. Because of the many varieties of LiDAR data, products, and applications, its cost may vary significantly from project to project. The most important question regarding LiDAR's cost is how will the data be used? LiDAR purchases should be based on a cost-benefit analysis. Cost differences begin with such factors as the project size and terrain, move through the LiDAR data quality itself, and all the way through post-processing to the choice of final deliverables. Some costs, like mobilization, may be fairly fixed. Due to this and general economy of scale, LiDAR costs per square mile go down with larger projects. For this reason, building consortiums with other users is advantageous. These are some average cost estimates per square mile for LiDAR of different vertical accuracies and point densities. LiDAR accuracy is stated as a distance interval with statistical confidence, such as a root mean square error, or RMSE. The lower the RMSE, the better the accuracy. LiDAR of better accuracy and higher point density tends to be more expensive. Data accuracy extends to related products as well, such as contours. Derived products can only be as accurate as the raw LiDAR data. This table shows the vertical accuracy requirements for LiDAR data in order to produce 1, 2, and 3-foot contour intervals under several different standards. Average costs for supplemental LiDAR products, such as intensity images and gridded elevation models, range from about $20 to $50 per tile. However, more labor-intensive products, such as contours, can be much more expensive depending on the requirements and applications. For example, the break lines shown in the middle of this chart are generally a necessary precursor to contours and can drive up the cost for those derived contours considerably. LiDAR may be applied to a wide range of projects and fields from flood maps to transportation. These are just a few of the ways in which LiDAR is currently used. New applications for LiDAR data are found regularly. LiDAR data has proven very useful in a number of watershed-related applications, including flood mapping. The LiDAR point density necessary for flood mapping is relatively low, about 5 meters. The Federal Emergency Management Agency, or FEMA, requires digital elevation models derived from LiDAR to meet the national standards for spatial data accuracy of 15 centimeter RMSE, or about 1 foot total accuracy. This map compares LiDAR and FEMA Q3 flood mapping data in North Carolina. The green area shows the LiDAR data floodplain, the red area shows the older FEMA Q3 zone, and the blue line is the actual river center line. The redelineation of the floodplain by the LiDAR has taken into account the elevated road running through the plain. The LiDAR data has also reincorporated the river center line into the floodplain. Highly accurate elevation is important for portrayals of flood risk in coastal areas as well, in particular when dealing with extreme events such as hurricanes. This LiDAR-based elevation map shows Charleston, South Carolina at mean sea level, then at mean high water level, and finally what would have happened if Charleston had taken a direct hit from Hurricane Hugo in 1989. Forestry applications have also benefited from LiDAR. Some current applications include timber volume calculations and fire modeling. LiDAR for forestry can be more expensive because it usually requires a relatively high point density to penetrate the forest canopy. LiDAR can aid in the calculation of timber volumes by providing accurate data on forest cover, tree heights, crown size, and spacing over large areas. Tree volumes can be calculated through empirical relationships based on these factors. Much of the same data is applicable to fire modeling in forests. For example, the height to the base of the live canopy in a forest is an important parameter for modeling fire risk. LiDAR can be used to estimate this height by classifying pulse returns from the forest canopy. LiDAR is also useful in transportation and infrastructure. It's been applied in a variety of transportation, cadastral, and emergency management projects. LiDAR is proving to be very useful and less expensive than traditional techniques in transportation planning phases in particular. For example, LiDAR has been used to help design transportation drainage systems and for environmental impact statements. Traditional engineering and photogrammetrics are still necessary, but as LiDAR evolves and techniques improve, it will continue to grow as a transportation tool. Classification techniques also make LiDAR a very useful tool in cadastral and other infrastructure fields. For example, using LiDAR data, building footprints can be delineated by successive classification and eventually extracted as vector features. This technique is not perfect and requires additional processing in most cases, but is generally less labor-intensive than many traditional methods, such as digitizing from orthorectified imagery. These extracted features can also be recombined with bare earth terrain and draped imagery, producing a very realistic three-dimensional representation. Among other fields, three-dimensional city models are useful for emergency management. LiDAR is not a solution in itself, but it can be a very important part of the solution to many complicated problems in a wide variety of fields. LiDAR is not cheap, so knowing how it will be used is the first step in a cost-benefit analysis to determine needs. As with most products, LiDAR is cheaper by the dozen. It is generally cheaper per square mile for larger projects, so working with others to share the cost is beneficial.